we're going to be starting our kinetics discussion with reaction mechanisms, something of an unusual place to start, but a good idea I heard from a great teacher named Lisa McGoss. So let's take a look at this. Now, when we have been writing our chemical reactions, we write an overall reaction like that. And what this does is it depicts the beginning of our process and it shows the end of the process. Very valuable. Gives us the overall balanced stoichiometry. And it's quite helpful, as you've already seen in your lab, for studying things like percent yields and for determining quantity requirements for reactions. We're going to use it to study changes in energy, particularly the heat released or absorbed in a reaction called the enthalpy. We've seen that term before. A term with which you may have vague memories is entropy, the idea of disorder in a reaction, and we'll spend more time on that. But those all begin or all really depend upon just the beginning and the end of a reaction. And when we look at kinetics, it really begins to focus on how a reaction occurs. And I think if you evaluate this reaction, you'll see that the probability that three molecules will collide simultaneously, right? Collision theory, simultaneously with the correct energy, that in and of itself is not very likely, but it also has to have the correct orientation. And it's not just about getting two molecules into the correct orientation, it's about getting three molecules into the correct orientation. So what we want to take a look at in a reaction mechanisms is how do these molecules react on a more molecular level? How do changing concentrations, so we're going to focus quite a bit of our attention on that, and some other conditions, such as temperature, adding a catalyst, how do those alter the rate with which the reaction comes to completion? And a mechanism, I think, will help us understand that very effectively. So let's take a look, and we'll keep forging ahead. I want you to notice as we're doing these that the page number is down in the bottom right-hand corner. So the page number of your notes, that might help you keep track a little more effectively with this. Now, a reaction mechanism addresses those concerns that we have, trying to address what happens at the molecular level. Which bonds are being broken, which bonds are being formed, and in what order is all of that happening? And this is suggested this is formed by suggesting a series of, this is a keyword. Now, there's a vocab list at the end that can help you because there's a lot of terminology here. And we're going to look at a series of elementary steps by which collisions and then the overall reaction occurs. It's sort of like marking out the path that you take to school. The beginning and the end is home to school. But you may not go directly from home to school. You may first go from home to pick up a friend at a friend's house, and then you two may stop at the 7-Eleven to pick up an energy drink or maybe a cup of coffee, and then from there you may make it to school. So this overall beginning and end would be your overall stoichiometry, but these steps here would be the mechanism that is involved. Now, when we talk about mechanisms, scientists typically come up with them in what is called a semi-empirical method. Empirical means experimental. So what scientists use is a combination of experimental data. So we are going to rely on experiment. We're actually going to analyze data, which I think is the most powerful part of doing kinetics at this level. And they also bring in their knowledge of the theory and their understanding of how molecules behave. Now, as we evaluate whether a mechanism is plausible, Now, note that we're not saying that this is the mechanism. All we're saying is, man, this looks like I could study it further. It looks worthy of more time on our part. And the first criterion is the elementary steps must add up to the correct overall stoichiometry. So we would have to get whatever the mole ratios were in the original overall stoichiometry. Now, additionally, the mechanism has to agree with something we call the rate law expression. The rate law expression is a mathematical equation that describes how the rate of a reaction is going to depend on molarity and partial pressure, depending on what values are given. Now, there's also kind of hidden in there a little discussion on temperature, and we'll move through that as we move through all of our notes here. Now, let me give you an idea of what our goal is with this. So here's our overall reaction again. Now, if, for example, we doubled the concentration, now those square brackets mean concentration measured as a molarity, moles per liter value. Now, if we double that and the rate doubles, that means that there's a 1-to-1 proportionality or a direct proportionality, and we would say that our rate is proportional to our concentration of NO2 to the first power. Now, if we doubled NO2 and the rate quadruples or increases by a factor of 4, then we would say that our rate is proportional to, let's just keep that proportionality in there, NO2 squared, right? Because if you double it, 2 represents doubling, and if we square it, that's the impact, then our rate would increase by 4. If we double NO2, and this is interesting, if we do that and the rate remains unchanged, then what we can say is that the rate indeed does not even depend upon our NO2 concentration. And that's where mechanisms help you understand that early on in the game. How is it that a substance could show up as a reactant but not impact the rate? That's a pretty critical answer that we want to move towards. Now, in this case, if we wanted to be explicit, we would say that the rate is proportional to NO2 to the 0 power. Okay, so 2 to the 0 power is 1. So the old rate and the new rate are the same. And now, these values that I've been referencing here, this 2 in the power, this 1, this 0, how a rate is affected by a concentration, the word that we use is order. These are the orders of the reaction, and we're going to talk about them with respect to a particular reactant, and then we'll talk about overall order as well. Now, the order is given by elementary steps or steps. So it could be one elementary step, or we could be combining some steps, but this is key, paramount. It is not given by the overall reaction stoichiometry. In other words, I can't look at this reaction stoichiometry and say, well, there's a 2 in front, therefore it must be second order, and there's a 1 in front, therefore it must be first order. If this is an overall, not an elementary, I can't say that. I can't say that at all. That's not how we get our orders. Okay, so unfortunately, that doesn't happen. Fortunately, we can from an elementary step, because that does tell us just exactly how it reacts. Now, let me show you a little bit of terminology here as we build into this. Now, If I have one substance that might simultaneously decompose, for example, and it goes to products. Now note I'm talking about elementary steps here, not overall stoichiometries. We call that unimolecular. Now we can obtain a rate law, and since that's a 1 there, and since it's elementary, I can say the rate is equal to K times A to the first. And I would call that first order with respect to, that WRT is with respect to my molarity or concentration of A, and the overall would be first. Okay, now if it was bimolecular, meaning 2 molecules, and notice that we're only going on the reactant side of arrows here, we'd have A plus A, which is really 2A. So our rate is going to equal a constant times A to the second power. So we say it's second order with respect to A. And since that's all we have, we would call that second order overall. Now, A plus B, going to products, again, all we're doing is looking at the reactant side of an arrow. Rate would equal a constant. We'll see a lot more about that later. Molarity of A, molarity of B. Now notice there's a 1 for the A implied and a 1 for the B. So it's first order with respect to A, first order with respect to B. Now, the overall is the sum of those 2 orders. Okay, so it's the sum of all orders. Really helpful for scientists to understand what's going on. Now, in that unlikely event that it's termolecular, we don't use trimolecular. It'd be lovely if we did, but we don't. As scientists, the term is termolecular for 3. I have 3 possible scenarios for 3 molecules colliding. In this, I have 3A, so it would be K times A cubed, third order with respect to A, third order overall. In this case, again, remember, we're always deriving the rate law expression from the reactant side of the arrow. So rate, there's my K, that's just a constant. That constant turns the proportionality into an equality. It's first with respect to A, because of the 1, implied 1. Second with respect to B, we add those up, and that gives us third order overall. And then A plus B plus C is first with respect to each of these. And so first order with respect to A, first order with respect to B, first order with respect to C, and that's going to give us an overall third order reaction. Now, before we try this, I want to give you just a brief introduction and fill in just a few more blanks for the end of this little video clip. So what we're going to do, we are only going to solve 2 ways. There's many, many, many ways, but Chem 1 is an introduction. So we're going to look at 2 types of mechanism. One has a slow step, and the slow step is going to dictate the rate of the reaction. Just like in one lane, the slowest car is going to dictate how fast it can go. So the slow step is called the rate determining step. And then the overall rate cannot be any faster than the slowest step. And then we want to talk, I'll delve into this just a little bit more, but we're going to talk about one elementary step reaching a very fast equilibrium. That means that the forward rate is equal to the reverse rate, and it appears as if the reaction has stopped. Now, we're going to work on a couple of these and get some more terminology. So until then, this is signing off.